In this, we are going to see the conversion of epsilon-NFA to DFA. Previously, we have seen epsilon-NFA to NFA conversion, and in the previous lectures, we have seen NFA to DFA conversion. Now, this is another method where directly epsilon-NFA can be converted into DFA. So, I am going to take the same example that we have discussed in the epsilon-NFA to NFA conversion. So, here Q0 is the starting state. Upon Q0, if you provide 0 input then it will be there in the Q0 itself. Then going to epsilon with the epsilon production Q1, and on 1 it is resulting into Q1. So this is the same diagram that we have considered in the previous lecture. Next, in this step 1 is construct the transition table for epsilon-NFA. The general transition table that we'll draw for any NFA or DFA, in the same way we'll get to construct the transition table for the epsilon-NFA. So here the transition table dou E is for the epsilon-NFA is here Q0 is the starting state, Q1 and Q2 is the final state, where I have marked as star. So star is the final state and arrow mark represents the starting state. So Q0 on 0, where it is going? To the Q0 itself. Q0 on 1, it is going to null state because there is no transition for input 1. Next, Q0 on epsilon, it is going into Q1 state Q1, right? So this is the simple state transition table. Next, Q1 on 0, since on Q1 there is no possible input 0 here in the diagram, so hence it is resulting into the null state. Q1 on 1, it is going into Q1 state. Q1 on epsilon, it is moving into the Q2 state. Now Q2 on 0 is resulting into Q2 itself. Q2 on 1 resulting into Q2 itself. And Q2 on epsilon, since on Q2 there is no possible input as epsilon, hence there is a set called null set. That means it is not moving to any place. So this is a simple transition diagram. That is called epsilon E here. Sorry, dou E here. Now compute the epsilon closure for each state. So here the Q0, Q1, Q2 are there. Compute the epsilon closure for each state. This is step 2. So epsilon closure of Q0, we know that the epsilon closure of any state, it is the itself, and what are the other states will visit with epsilon. So Q0 is the starting state, which is where we are going to calculate the epsilon closure. So epsilon closure of Q0 is itself, that is Q0, and with epsilon we are going to Q1 as well as Q2 state. So this we are going to include in the epsilon closure. Next, epsilon closure of Q1. So we know that epsilon closure of any state is itself, that is Q1. And with Q1 on Q1 epsilon, you are going to Q2. So Q1, Q2. Epsilon closure of Q2. So on Q2 you don't have any input as epsilon. So since any epsilon closure of any state itself, so here epsilon closure of Q2 is Q2 itself. So now the step 1 is over. Step 1 is the construction of the transition table. Step 2 is the construction of the epsilon closure. So these 2 steps are, I think by this time you have understood. Then we'll move on to the step 3. Step 3 is start with the epsilon closure of the starting state in epsilon-NFA and construct DFA. So start with epsilon closure of starting state in epsilon-NFA. So what is the starting state in the Q0? So Q0 is the starting state. What is the epsilon closure of the Q0? So epsilon closure of Q0 is Q0, Q1, Q2. So take it as a starting state. Okay, take it as a starting state and construct the DFA. So now we are going to form the transition table for the DFA, which is called dou D. We are going to call it as. So in which start with the epsilon closure of the starting state. So what is the starting state here? Q0. Epsilon closure of Q0 is Q0, Q1, Q2. We'll consider this as the starting state. Q0, Q1, Q2. Now, the procedure of calculating the constructing the DFA is like this. Now, dou D of Q0, Q1, Q2 we need to fill this particular transition table. So Q0, Q1, Q2 upon 0 for the dou D, that is dou D means the transition of Q0, Q1, Q2 upon 0. So how to compute this? Dou D of Q0, Q1, Q2 upon 0 is epsilon closure of, this is the formula here, we are supposed to make use of epsilon closure of dou E of Q0, Q1, Q2, comma 0. What is the dou E? Here this is the dou E. That is the transition table in the epsilon. So dou E of Q0, Q1, Q2, comma 0. So the epsilon closure, this can be elaborated like this. Epsilon closure, this is as it is. And this can be elaborated like this. Epsilon, that is dou E of Q0, comma 0, union dou E of Q1, comma 0, union dou E of Q2, comma 0. Now, what is the dou E of Q0, comma 0? Dou E of Q0, comma 0 is Q0. This is the Q0. Next, dou E of Q1, comma 0. Dou E of Q1, comma 0 is null set. And dou E of Q2, comma 0. Dou E of Q2, comma 0 is Q2. Right? Now, Q0 union empty set union Q2. Obviously, the resultant is Q0, Q2 itself. We all know that epsilon closure of Q0, comma Q2 is equal to epsilon closure of Q0 union epsilon closure of Q2. So, epsilon closure of Q0 is, we have already calculated Q0, Q1, Q2. So, Q0, Q1, Q2 union epsilon closure of Q2 is Q1, Q2. Anyhow, this Q1, Q2 is covered in the epsilon closure of Q0. So the resultant value is, resultant set is Q0, Q1, Q2. So we are going to place the same here. Dou D of Q0, Q1, Q2 upon 0 is Q0, Q1, Q2. The same thing you need to apply for 1 also. So dou D of Q0, Q1, Q2, comma 1. So which is, the formula here is epsilon closure of dou E of Q0, Q1, Q2, comma 1. So how you will split it? Epsilon closure of dou E of Q0, comma 1 union dou E of Q1, comma 1 union dou E of Q2, comma 1. So dou E of Q0, comma 1 is, dou E of Q0, comma 1 is null set union dou E of Q1, comma 1 is Q1. So we are going to place Q1 here union dou E of Q2, comma 1 is Q2, comma 1 is Q2. Now empty set union Q1 union Q2. So Q1, comma Q2. Now epsilon closure of Q1, comma Q2 is again, epsilon closure of Q1, comma Q2 is, so epsilon closure of Q1 is Q1, comma Q2 union epsilon closure of Q2 is Q2. So anyhow it is union. So Q1, comma Q2 is the resultant value. So thereby Q0, Q1, Q2 upon 1 is going for Q1, Q2. Next, like that, Q1, comma Q2 upon 0. So we are going to get as Q2. Q1, comma Q2 upon 1. The same procedure will follow here, so that we'll get Q1, Q2. And here on Q2, if you supply 0 as the input, it is resulting into Q2, and Q2 on 1, it is resulting into Q2 itself. Now, we all know that the construction of the DFA, in which whatever is the final state available in the epsilon-NFA, that final state containing states must be considered as the final states. So here in this state, in this set, we have the Q2, so hence it should be made as final state. So that reason it is a starting state as well as the final state. It is indicated by star. Q1, comma Q2, in which Q2 is the final state, so hence the entire set should be the final state. So that is the reason it was marked as star. and Q2 is the state which itself is the final state. So hence this is also marked as star. Now construct the DFA from the transition table. Now Q0, Q1, Q2 is the set. This is the final state and itself is the starting state. On this, if you supply input as 0, then it is again resulting into the same state. If you supply input as 1, then it is moving on to the Q1, Q2 as the state. So here Q1, Q2 is the set which is again a final state, since the Q2, which is the final state in the NFA, was available. Now Q1, Q2 on 0, it is going to Q2 state. Q1, Q2 on 1, it is remaining on the same state. Now on Q2, either you give the 0 or 1, it is resulting into the same state. Now you look at, now it is further improved from the epsilon-NFA to NFA, epsilon-NFA to DFA, in which for any given input, it is going into a specific state. So for example, we'll consider Q0, Q1, Q2 as state A. Now on A, if you supply 0, it is resulting into state A itself. Like previous diagrams, it is not going into multiple states. So hence this is true for all states in the given transition diagram. So hence it is a DFA, deterministic finite automata. So in this lecture, we have seen the conversion of epsilon-NFA to DFA.